Good morning. My name is Thibaut Devolder, and it's my pleasure today to present you our work about the question whether we can measure a population of incoherent spin waves by just looking at the noise of an inductive antenna. This is a work that has been done in my group in C2N, Palaiseau, France, in collaboration with Solignac in Paris-Saclay, France. Essentially, the motivation is the following. In magnetic devices, we generally manipulate a population of coherent spin waves, but in addition to this coherent spin wave that we intend to manipulate, there are parasitic spin wave populations, either the thermal populations or additional populations that are not wanted. And the question is whether they will affect the noise in the spin wave receivers and whether we have to take that into account. So our goal today is to try to see whether we can measure these incoherent populations in a non-invasive manner using inductive antennas. So the standard device for this study is the following. We will use a film that is a synthetic antiferromagnet made of cobalt, iron, boron, and ruthenium, and we will essentially look at one of the two eigenmodes of the system, which is the acoustical spin wave branch. We will pattern this film into a device which will be a spin wave conduit below which we will have placed two inductive antennas. In the end, we will only need one, but first we generate two antennas because this is useful to check the properties of the device. So to check the properties, we place the sample in a probe station and connect one antenna to an input source and the other to a receiver, a VNA. And we use the first antenna to generate spin wave, and we collect them using the second antenna. And by doing that, we can record the antenna-to-antenna transmission parameters versus frequency and versus field. And as expected, in the region above the ferromagnetic resonance, we do have finite transmission of spin waves with a phase that alternates between positive and negative simply because when we increase the frequency, we increase the k-vector, so the phase rotates upon propagation. So this indicates that this device properly measures spin waves in the spin wave conduit. So now the question is, instead of using an intended spin wave population generated by an RF pump, can we use the same antennas to measure the thermal populations of spin waves or the non-coherent population of spin waves present in the sample in the absence of RF pump? So for this, we do not generate spin waves, we just rely on the fact that there are spin waves already present at room temperature in the system and that they navigate below the antenna such that they generate stray fields that can be inductively measured by the antenna. So in order to measure this stray field, what we do is we place our sample into the following experimental setup. So the sample is an electromotive force and an output impedance, and we send the signal that it generates to an amplifier and then to a spectrum analyzer. If we do that for a given field, we obtain this kind of spectra, so the power spectral density versus the frequency. And at some specific field where we expect the FMR to be here, in fact, we don't see much in the experimental raw data spectrum. To reveal the magnetic signal, we have to do subtraction and look at the excess noise at this field compared to another reference field. And if we do that, we can see that there's no excess noise in the spin wave gap, but as soon as we are above the spin wave gap, we see a strong signal that seems to be related to magnetism. Indeed, if we look at this excess noise versus frequency and field, it has a kind of Kittel relation that looks like very much the one we measure on the same device by VNA FMR, which is this brand for the acoustical spin waves. So the question is now, what is the origin of this magnetic signal? Is it the inductive noise due to the thermal magnets, or is it something else? So to answer this question about the physical origin of this signal, let's look again at the experimental setup. In this setup, any noise coming from the device flows to the amplifier and is measured. And to look at the origin of this noise, we will modify this setup into a second configuration where instead of sending the signal directly, we will send the signal through an isolator, okay, that passes the signal in the frequency of a phone. If we do the same experiment with this modified setup, now the excess noise doesn't show any magnetic features perceivable at the ferromagnetic resonance. So this is somewhat puzzling, because if the signal was originated from the inductive noise generated by the spin wave populations, then it would equally flow to the receiver in the first device from left to right, and in the second configuration from left to right. So if this is measurable in one configuration and not in the other, it means that this magnetic signal that is present in the noise of the receiver is not due to spin wave population. So what is it then? So if it's not due to the spin wave populations, it's due to other sources of noise. And the other source of noise in the device is the Johnson-Nyquist noise, related to the fact that the antenna is a conductor. So as any conductor, it will have voltage fluctuations according to the Johnson-Nyquist theory, with a power spectral density that is proportional to the circuit temperature and to the impedance of the device, which comprises a resistive term, but also an inductive term proportional to the magnetic susceptibility. So if you think about it, in the first experimental configuration, any noise coming from the sample goes towards the amplifier, but here there's a mismatch plane, an impedance mismatch plane, so it's partially reflected, and it's also partially reflected here as the mismatch plane between the sample and the sender. So we have some sort of microwave cavity, okay, in which microwave standing waves can build up. And their amplitude and phase will depend on the reflection coefficients at the two mismatch planes. So if we now change the frequency and go to magnetic resonance, then the inductive part of the impedance of the device will change. So the reflection coefficient here will change, and the amount of standing microwaves will change. In contrast, in the second configuration, we only allow energy to flow from the device to the amplifier because of this isolator that forbids the reverse transmission of the signal. So by doing that, we effectively suppress the microwave cavity so that there's no standing waves any longer in the devices, even if you change here the reflection coefficient at the resonance or being away from resonance. Because this mismatch plane is compensated, the now excess noise is now flat. Okay. And this is what happens in this configuration. Okay. Only the Johnson-Nyquist noise is not amplified by any cavity effect. And indeed, if we model that, that is to say, if we take the frequency dependence of the impedance, so of the magnetic susceptibility, and the impedance of the different elements in the circuit, the model that includes only the electronic noise accounts very well for the total excess noise measured experimentally. So if I summarize my talk, if we want to measure an incoherent spin wave population in the devices using an inductive antenna, we will look at the total noise and see how it varies with the magnetic temperature or equivalently with the population of incoherent spin wave. There are two sources of noise. One is the classical Johnson-Nyquist noise of the antenna, which comprises a magnetic signal due to the magnetic susceptibility, and it has a frequency variation that is wavy because of unavoidable mismatch planes in the sample. On top of that, there's a noise due to the population of magnons. Okay. It scales linearly with the temperature, with the magnetic temperature. It also has impedance mismatch terms that are roughly of the same form as the Johnson-Nyquist noise, so that if you are at room temperature, since the Johnson-Nyquist noise dominates and since they have similar frequency dependence, it's going to be very difficult to measure the population of spin wave if this population is at thermal equilibrium. In contrast, if you have an out of equilibrium population of spin wave, okay, then you can measure it if the equivalent magnetic temperature follows this formula, which typically, if we want order of magnitude, it means that it will be measurable if for a stripe width of 10 microns, you have, for instance, more than a population of spin wave that is 30 times over what it would be at thermal equilibrium. And with this, I invite you to look at the details in these freshly published publications, and I thank you for your attention.